Alright, thanks for watching, and in this video I want to give you an exciting glimpse into the world of the calculus of variations, which is actually a tool that's used to sort of solve PDEs, and it's a very exciting way of turning a PDE into a minimization problem, or in other words, a minimization problem into a PDE problem. So let's first solve a problem that at first glance has nothing to do with differential equations. So goal, find a function f, maybe continuous or something, function f of x, such that the following energy, and if you know physics, it's sort of like the kinetic, it's exactly the kinetic energy, 1/2 integral from 0 to 1 of f prime of x squared dx is smallest. Among all functions f, such that, because of course you might say, hey, what about the zero function? But let's give you a bit more restrictions, such that f of 0 equals to 0 and f of 1 equals to 1. In other words, you want to do the following. Among any function f, again smooth, not even differentiable almost everywhere would work, and f of 0 is 0 and f of 1 is 1. So think of a squiggly thing here, or maybe a parabola, or even a straight line, etc., etc. Among all those functions, you want to find the one or the ones for which this energy is the smallest. Okay? So for example, let me just give you a couple of examples. F of x equals to x cubed gives the following thing. I of f is integral, so 1/2 integral from 0 to 1, derivative squared, so 3x squared dx, which is 1/2 integral from 0 to 1 of 9x to the 4th dx, which is, 9/2 over 5, so 9/10. Antiderivative is 9x to the 5th over 5. So the energy of this function is 9/10. F of x equals to x squared, then I of f equals to 1/2 integral from 0 to 1 of 2x squared dx, and that's 1/2 integral from 0 to 1 of 4x cubed dx, which is 1/2 times x to the 4th, which is 1/2. No, sorry, it's 4x squared, which now gives you 4/3. Okay, sorry about that. 1/2 times 4/3 x cubed, so it gives you 4/3, which is 2/3. And you can already see, if you had to choose between the function x cubed and the function x squared, then x squared is a winner, because the energy, it takes less energy to calculate I with x squared than to calculate I with x cubed. So this is a better thing, right? And if you think about it, heuristically, the answer should make sense, because if you take I of f, again 1/2 integral from 0 to 1 of f prime of x squared dx, smaller the derivative is, or the smaller it moves, the better. Because, if f changes a lot, if it squiggles a lot, then the derivative squared becomes bigger, and if you integrate that, it's a problem. So intuitively, the best solution should be the one that doesn't move as much. Namely, intuitively, the minimizer of this energy should be the line connecting 0 and 1. But of course, we want to prove this, and we'll do this very soon. Let me just give you a little fact that we'll need in a second. So maybe that's part 1. So that was part 0, and now part 1. Okay. There's a little fact. Suppose you have a function g that is 0 at the endpoints. 0 and 1, and g looks like that. And suppose if integral from 0 to 1 fg equals to 0 for all g again continuous, with g of 0 equals to g of 1 equals to 0. In other words, if you test f with any function g and you get 0, then f has to be identically equal to 0 if it's continuous. Then f identically equal to 0, assuming f is continuous. And we will need this fact because we will essentially show that, if you test our function against a differential equation, you always get 0, so this function will be identically equal to 0. Let me quickly show that. It's a very nice proof. So why? Suppose f is non-zero. 0 for some x naught. X naught in the interval 0, 1. I'll talk about the endpoints in a second. Okay. Then, if it's non-zero, it's either positive or negative. Assume it's positive. X naught is positive. So we have this function here. This is 0, this is 1, and we know f is positive here. Well, because it's continuous, f also has to be positive in a neighborhood of x naught. So maybe in a neighborhood u. So because f is continuous, f is positive on some neighborhood NBHD of capital U of x naught. All right, so again, we have this neighborhood U, this x naught, where f is positive. And all you need to do is to define the following function, and you can do this using what's called bump functions. Define a function g that's just positive on u, and everywhere else is negative. Let g be positive on u, and 0 outside u, and g is continuous. In particular, because we're x naught is inside the interval 0, 1, g has to be 0 at the endpoints 0 and 1. In particular, g of 0 equals to g of 1 equals to 0. So, g is a very good test function that we can use. So, on the one hand, because g satisfies those properties, we know by assumption it equals to 0. On the other hand, because g is 0 outside of u, this integral is equal to the integral of u of fg. Okay, g is identically equal to 0 outside u. So the party happens in u. Okay, it's a cool neighborhood. But what do we know about u? We know that f is positive in u, and also g is positive in u. So this is the integral of a positive function, which is positive. And I'm positive about that. So what do you get? You get that 0 equals to a positive number, and that's a contradiction, at least in the real world. A contradiction with what? A contradiction with the fact that f is non-zero at a point. So f is identically equal to 0 on the open interval 0, 1. But what about the endpoints? It's actually just follows from continuity. So if, let's say, f of 0 is positive, then, right, because f is continuous, f is positive near 0. So in particular, f is still non-zero from some point near 0. So f is non-zero for some x0 near 0. And you can still use the same proof. Okay, very good. And that was to illustrate this technical fact that if you test a function against some other function g, and you get that it's always 0, then the original function has to be the 0 function. And this will be useful in a second. Okay, now we can play. Spielen wir. Okay? Because we can now solve our problem at the beginning. So part 2. Okay? Suppose f minimizes this functional. So I of f, which is 1/2 integral from 0 to 1 f prime of x squared dx. Our goal is, here's our game plan, we want to find a differential equation that f has to solve, and we want to solve that differential equation. That's why I always said this relates to the two partial differential equations. So now let g be arbitrary, and you'll see why I say that. Let g be arbitrary against smooth and arbitrary with, is g 0 at the endpoints. G of 1 equals to 0. And you'll see in a second why this is true. And consider now the following. And given f, and let's say some real number t, consider the following function. And before I write this down, I want to tell you something. This is a difficult problem, all right? Because among all the functions, you want to minimize this thing. So it's really a problem about functions. And it's very hard to do calculus on function spaces. But here's the cool thing about this. We will take this difficult problem and turn it into a one-dimensional calculus problem, which is why this problem is called the calculus of variations. Because if you have f and t, consider the following single variable function. H of t, which is the energy of f plus tg. Okay. Which is, if you want, 1/2 of the integral of f prime plus t g prime squared dx. Again, not dt, but t is a parameter if you want. And let's again also look at this picture. So this is t, this is 0. We know that f minimizes this thing, right? So, in particular, among all the values of t, I of f is the smallest one. And I like to remind you, I of f is h of 0. Which means that any other value of t that you pick, it cannot be the smallest one. At least locally, it can't be the smallest one. So if you pick another value here, I of f plus tg, because f minimizes this, it's possible that it's equal, but it can never be smaller if you want. So in particular, if you look at this picture, and let's say this is h of 0 and h of t, we can say for sure that h has a minimum at 0. That h has a minimum at 0. Again, because I of f is the smallest value. And now here's where the calculus comes in. What do you know about functions which have a minimum at the number? Well, it means their derivative is 0. It has to be a critical point. So h prime at 0 equals to 0. And this precisely, it's the passage from function spaces to single variable calculus. So now that we have this info, let's calculate h prime of t. Prime of t, right, that's d over dt. 1/2 integral from 0 to 1 of f prime of x plus t g prime of x squared dx. Again, stuff is smooth, so we can just pull everything inside of the integral. 0, 1, d over dt. F prime of x plus t g prime of x squared dx. And then let's just calculate that integral from 0 to 1. And remember, this is a function of, we want to differentiate with respect to t and not with respect to x. So there's no double derivative, double prime here. So it's really 2 times f prime of x plus t g prime of x, and then times g prime of x dx. And 2's cancel out. And as I said, we want to use eventually the fact that I've written down 10 minutes ago. And if you think about this, this is actually a very nice, job for Mr. or Mrs. integration by parts. So let's integrate this by parts. And again, I'm making a point here. So that's really f prime of x plus t g prime of x times g of x from 0 to 1 minus integral from 0 to 1, and now we put the derivatives on the x's, f double prime of x plus t g double prime of x, g of x dx. And here comes a cool thing. Remember, what is g? It's a function that's 0 at 0 and 1. So it's 0 here and 0 here. It could be, imagine it's positive, because it's for any g, okay? And therefore, if you plug in 1 and 0, you get g of 1 and g of 0, which gives you 0. So in fact, we chose the function g such that there's no endpoints, right? It's 0 at the endpoints. So in the end, the derivative of h of t becomes minus integral from 0 to t f double prime of x plus t g double prime of x, g double prime of x, g of x dx. That's h prime of t. And now, remember, we know that h prime of 0 equals to 0. So let's just plug in t equals to 0. So t equals to 0 gives you h prime of 0 is minus integral from 0 to 1 f double prime of x g of x dx. And remember, you know that this is 0. So what we get now is minus integral from 0 to 1 f double prime of x g of x dx equals to 0. And here's an important thing. This is true for any function g. Right? Remember, we want to find f, and this is arbitrary. So this is true for any g. Any g, in particular positive ones, with g of 0 equals to g of 1 equals to 0. So by the fact, so use fact, what this fact says is that this function has to be precisely equal to 0. So by the fact, we get that minus f double prime of x equals to 0. In other words, the solution of our minimization problem has to satisfy the following differential equation, which here in general it's called the Euler-Lagrange equation. In this case, ODE, but in general it's a PDE. And notice, Euler and Lagrange, they're two very important names, and if a theorem is named after really important people, it's very important. So it's a very important differential equation. And in general it's hard to solve, but here it's not too bad. We get f of x, if you anti-differentiate twice, has to be a linear function, but remember f of 0 is 0 and f of 1 equals to 1, and the only function that satisfies this is f of x equals to x. So particularly if your function is smooth and it minimizes this energy, then it has to be the linear function. But just a little bit careful, because we assume that f is, differentiable, but it turns out, and this is, I think, in a very nice research field, is to find non-differentiable solutions to this. And in fact, for example, the zigzag function here from 0 to 1, it actually also satisfies this what's called this energy. It's also another minimizer of the energy, which is super exciting, because in this sense you can find non-differentiable solutions to this. So you have more generalized solutions. And again, the exciting thing was we took this minimization problem and turned it into a differential equation. And in fact, for the last part, I just want to show you, you can generalize this to higher dimensions. So part 3. So suppose, here's a little fact. If f minimizes the following functional, I of f, which is 1/2 integral of u, the gradient squared dx. So compare this with 1/2 integral of f prime of x squared. Literally the n-dimensional analog of this. And u is an open-bounded subset. So u is open and bounded in Rn. And suppose that f is equal to some given function on the boundary. And f equals to g given on the boundary. This is if you want the analog of f of 0 equals to 0, f of 1 equals to 1. So if you have your set here and you have a boundary and you impose that f equals to g, some given function, then f turns out to solve a very important PDE, namely Laplace's equation. So then f solves minus Laplacian of f equals to 0 in your set, and f equals to g on the boundary. And surprisingly, the proof is exactly the same. Namely, you just pick some other function, I guess g, or not quite g, but like g squiggle, and you consider h to be I of f plus tg, and then you do the same thing where you differentiate, and in the end you get this Laplace's equation, which again helps us find solutions to Laplace's equation. Just find minimizers of this functional. And you might also ask why in the world this is important, because here we're lucky because it turns out we can solve Laplace's equation, not a problem at all. But sometimes you have PDEs that are extremely hard to solve, and there's no way to even get a formula with this. Well, if somehow you can say that this has to be a minimizer for some energy, then sometimes it's easier to find the minimizers of energies. And once you have that, maybe you have hope of finding solutions to PDEs. Let me give you a specific example. Suppose you want to solve this. Okay. To solve the following equation, sum from 1 to n of f of the ith derivative of f plus 1 plus gradient f squared, and you differentiate that with respect to xi. Good luck solving that, it's a very difficult PDE. It turns out this becomes, you can write this equation as the minimizer of some much easier functional. Easier to minimize the following one. I of f is, again, it turns out if you take the following minimizer and you find the Euler-Lagrange equation, the functional is just the following: 1 plus gradient of f squared dx. And if you remember your multivariable calculus, you may recognize this as simply the surface area of the graph of f. So if you have some graph of f and you find the surface area, then I of f gives you the surface area. Of graph. So instead of asking which functions solve this PDE, it's easier to ask which functions, again with some boundary conditions, minimize the surface area of some graph. And this actually leads to a very beautiful subject of area minimizing surfaces. And on the comment section or the description section, I will put some very nice links to Wikipedia where they give examples of area minimizing surfaces. And once you have those surfaces, those are automatically solutions to our PDE. So it's really nice, and I hope you like this little tour of the calculus of variations, which also, it's a very active subject area in math. And If you like that and other PDE things and math in general, please make sure to subscribe to my channel. Thank you very much.